Yeah, so today we have for the chat series, Henri Darmon from a distinguished James McGill professor at McGill. He's going to be speaking about explicit class field theory. Henri received his PhD in 1991 under the advisement of Dick Gross, which actually makes him the youngest of our chat speakers this year. So I think he's won numerous awards, including the Cole Prize in Number Theory in 2017. And his research spans many different central areas of number theories, quite a few papers, so it's a lot of impact. So from variants of FLT to, well, words involving Stark-Heegner and p-adic integration, modular symbols, p-adic Zagier, main conjectures and Euler systems and p-adic L functions. A lot of, so one thread that continues for much of his career is his work towards Hilbert's 12th problem, realizing explicit class field theory over, say, real quadratic fields, for instance. And I believe he'll be discussing that today. So we're very happy to have him.
So thank you, Romiar, for your nice introduction. So yeah, indeed, I'll be talking about explicit class field theory, which is a problem that's kind of been dogging me throughout my career. And so the problem basically is a bit of a loosely formulated, ill-posed question, which is motivated by two classical results in number theory, which it seeks to extend. The first is the theorem of Kronecker-Weber, which says that every abelian extension of the rationals is generated by roots of unity, in other words, the values of the exponential function e to the 2 pi I z at rational arguments. And the second result is what comes out of the theory of complex multiplication, which is that all or lots of abelian extensions of imaginary quadratic fields can be generated by values of modular functions at imaginary quadratic arguments. And Hilbert's 12th problem, roughly speaking, asked the question of, is there a class of functions that might play the role of the exponential or modular functions in generating all abelian extensions of a given ground field? So for the rationals and quadratic imaginary fields, you have a very satisfactory answer to that question. But for other number fields, the situation is much more murky. Now, I'm going to say a few words about what I'll be doing in this lecture. So what I want to do, following the format of the chat series, is to give a somewhat personal account of how my understanding of this problem, which is still extremely limited, has evolved over the years. And the point of view I'll be taking is very much a personal one and a chronological one, rather than a logical one, which is one of the nice features of this lecture series, that one can focus on the somewhat indirect, roundabout ways in which ideas come to us in practice. When we come up with a final result, we tend to write it up in a very clean way, with hiding all the false starts and wrong directions and dead ends that we followed before arriving at the final result. So I'll be trying to bring some of that out in this lecture. Okay, so I want to begin by my early influences. So the period 1987 to 91, which were my graduate student years at Harvard. So, of course, this was a wonderful time in period to be studying elliptic curves. There were many important results that had been freshly obtained and were very much in the air at the time. The first was Carl Rubin's proof of the finiteness of Shafrovich-Tate groups, which I think dates back to around 1986, or maybe a bit earlier. I remember a conference in Quebec City where Carl gave a series of plenary lectures on this topic, and that was the summer right before I started at Harvard as a graduate student, and that inspired me very much, and certainly played a role in solidifying my resolve to study elliptic curves when I arrived at Harvard. And then, of course, there was also the Gros-Zagier formula, which had also been obtained a few years previously, and which has been very much at the center of what I've been doing ever since. And then there was a result of Kolyvagin, which I think came out around 1987. Maybe we were more aware of it around 1988 or 99, which gave a spectacular arithmetic application of the result of Zagier and used the Heegner points and their non-vanishing to get tight control of the arithmetic of elliptic curves. And the most striking result was a proof of the weak form of the Birch-Renten-Dyer conjecture for all modular elliptic curves of analytic rank 1. At that time, it was important to specify that the elliptic curves were modular. And then there were other things as well that were sort of wafting in the air in the corridors of Harvard at the time. I mean, there had been a seminar on tame refinements of BSD type conjectures, Maser-Tate conjectures in 1986, so right before I joined Harvard, and there was still a strong interest among various students in the Stark and Gross-Stark conjectures. And then finally, there was another beautiful result towards the Birch-Renten-Dyer conjecture, which was obtained by Coates. It was sort of more towards the end of my graduate student days. I think it came out in 1991, this strategy. And it didn't affect me very much because it took me much longer to really understand what was going on there. So it was only quite a few years after that I managed to understand this. Okay, and I also want to talk about some other results which influenced me very much during these years, and which might be a bit less known but which also had to do with the arithmetic of elliptic curves. One of them was a very tantalizing formula of Carl Rubin, which concerned the construction of rational points on CM elliptic curves via leading terms of p-adic L functions. So if E over Q is a CM elliptic curve, say by having CM by an imaginary quadratic field of class number 1, then the Hasse L function is related to the value at the center, say, is related to the value at 0 of a certain Hecke L function of a Hecke character by work of Doring and Hasse and so on. And this character is of affinity type 1, 0, which means that its values on principal ideals will be congruent to 1 modulo a certain conductor is equal to the generator of that principal ideal. And such a character always has a complex conjugate, which one obtains by just replacing alpha by alpha bar. And as far as the complex L series are concerned, these two L functions of psi and psi star typically give rise to the same Euler product, at least if the conductor is rational. But there's also a p-adic analog of this Hecke L function, the so-called Katz p-adic L function, which is defined by p-adically interpolating the special values of the Hecke L function. And that has a certain domain of interpolations. There's a set of characters for which, after dividing by suitable periods, one then defines the p-adic L function by p-adic interpolation. And one can set it up so the character psi is in the domain of classical interpolation. So the L function of E at 1 at the center is this classical value, which can be interpreted up to a simple non-zero multiple involving a p-adic period as the value of the Katz L function at the character psi. Now, Rubin's formula concerns the value of the same p-adic L function, but at the character psi star, which lies outside the domain of p-adic interpolation of the L function. And it says that there's a global point in the Mord-Helvig group of this elliptic curve, maybe tensor with Q, such that the value of this L function at psi star is the square of the formal group logarithm, the p-adic formal group log of this point, times a suitable p-adic period. And later, I think Bernadette Perrin-Riou proposed a similar formula for non-CM elliptic curves, for modular elliptic curves, but without complex multiplication. And these two formulae suggested at the time, I mean, a very tantalizing approach to the construction of rational and algebraic points on elliptic curves via the evaluation of p-adic L functions, or so via leading terms of L functions. We could take the leading term of suitable p-adic L function, take its square root, exponentiate, and then would obtain, at least modulo torsion, a generator for the Mord-Helvig group of elliptic curves in certain favorable situations. Now, this is exactly the same way that Stark constructed his conjectural units in abelian extensions of number fields. And that was the basis for his conjectural solution to Hilbert's 12th problem for totally real fields. And so that gave rise to a natural program, which was to extend Stark's conjecture to elliptic curves in order to produce preferably new algebraic points that wouldn't be able to obtain otherwise. Now, in the settings of the formula of Rubin, of course, the global point was ultimately obtained from a Heegner point construction. But one could hope that this general framework would be more widely applicable. That was one of the, anyway, that was certainly the idea that this gave rise to in my mind when I first heard of this formula of Carl Rubin. I think Carl was visiting Harvard one semester when I was still there, and I remember running into him in the hallway, and he sort of explained to me this formula before it had actually been written up, and that was a very exciting experience to me. Now I'm going to make perhaps a jarring transition from the sublime to the mundane by mentioning also a result that I obtained during these years at Harvard, one of my first mathematical results, which concerns an extension of the result of Kolyvagin. So here I consider the situation where H is the Hilbert class field of an imaginary quadratic field, and E is an elliptic curve satisfying a suitable Heegner hypothesis, which is not very important, just meant to ensure that there are Heegner points on the Mordell-Weil group of the elliptic curve over this Hilbert class field. And then a theorem that Bertolini and I obtained in 1989, so sort of in the second year of graduate school for me, was a theorem that says that if chi is a character of the Hilbert class field, and the order of vanishing of the twisted L function of E over K by this character is 1, so that L function has a simple 0 at the center, then the dimension of the corresponding chi isotypic eigenspace for the Mordell-Weil group is equal to 1. This is sort of the thing you would expect from an equivariant version of the Birchens-Rinton-Dyer conjecture. And the Gros-Zagier formula implies that when this L function has a simple 0, the sort of chi component of the Heegner point is non-trivial. So the rank of this dimension is at least 1 by Gros-Zagier. And then applying the descent method of Kolyvagin, one could prove a corresponding upper bound and get this equality. So this result was a very minor extension of the result of Kolyvagin. I only mention it for two reasons. So it had an important, it was important to me on a personal level. Firstly, because it was my first collaboration with Massimo Bertolini. He's been a very close collaborator over the years. I think by now we've written more than 35 papers together. It's been a very enjoyable and fruitful collaboration. And secondly, this very shallow result, I mean, modulo Gros-Zagier and Kolyvagin, of course, it suggested to me an interesting open question, which was a question that kind of obsessed me later over the years, although at the time I could do very little with it. And the question is this: if you consider now the case where we simply replace the imaginary quadratic field K by a real quadratic field and let H be its Hilbert class field, then it's easy to put yourself in a situation where the signs in the functional equations of the elliptic curve over K, twisted by all the characters of H, have odd order of vanishing because of the functional equation. And that happens when the elliptic curve satisfies a so-called modified Heegner hypothesis. I'll get into that later when I maybe go into a little bit more detail. And that implies this hypothesis that these orders of vanishing are all odd. In particular, if they're odd, they're all greater or equal to 1. And that means that the L function of E over the H, over the Hilbert class field, vanishes to order at least the degree of H over K, since it's a product of this many L functions, each having a simple 0 at the center. And if you believe the Birchman-Dyer conjecture, then you expect that the rank of the Mordell-Weil group of E over H is at least a degree. And then, in fact, one has some idea about how the Galois group should act on this Mordell-Weil group. It should essentially be, after tensing with Q, a copy of the regular representation of the Galois group of H over K. Okay, so the question then was, how can one construct the systematic supply of points that are predicted by the Birchman-Rinton-Dyer conjecture? And in light of the strong arithmetic applications of Heegner points that arose in the work of Gros-Zagier and Kolyvagin, we had a strong desire to kind of extend those constructions beyond the CM framework. Okay, so that's it about my first 4 years at Harvard. I spent the next 3 years of my career at Princeton. And my first 2 years in Princeton, I remember as being very, fairly quiet. In fact, I remember a conversation I had towards the end of my second year with Larry Washington, who was telling me, well, you know, the arithmetic of elliptic curves have been so many fantastic results, Rubin, Zagier, Kolyvagin, and so you've really been spoiled in these last years, and you can't expect that this is gonna keep going. I mean, you're gonna, at some point, things are gonna slow down, and we're just gonna have to take stock of what's happened, and maybe progress will come in other areas. And that was, I think that conversation took place in March of 1993, and we all know what happened a few months later. So in June 1993, there was a spectacular announcement of Coates Wiles, which was the proof that all of the solution of Fermat's last theorem based on the proof of the Shimura-Taniyama conjecture. Now, so my last year at Princeton was very exciting. We were all kind of scrambling to learn these new ideas. Yakov Sinai asked me to write an expository article about Wiles' proof for the Russian math survey. So I kind of dropped everything that I was doing, which was not very interesting in any case. And I spent the last year just learning about Wiles' proof. And one of the key ideas that I learned about in that year was the notion of deformation theory of Galois representations and modular forms. So that had been introduced already before when I was a student at Harvard. Mazur had introduced these ideas, but they had certainly gone completely over my head. I think a lot of people overlooked them until Wiles showed the spectacular applications that these ideas could have. Okay, so then after these 3 years in Princeton, I joined the faculty at McGill. And I would say the first 5 years at McGill were probably the time when I started to take the first serious steps towards this better understanding the elliptic star conjecture. And that began with a fairly modest project with Massimo. We were still working a lot together at the time. And the aim of this project was to transpose the p-adic Birchon-Swinnerton-Dyer conjecture that had been formulated by Mazur, Tate, and Teitelbaum for the cyclotomic ZP extension of the rationals, and to extend this conjecture to the anti-cyclotomic setting. So that was a very natural thing to do in light of all the work of Zagier and Kolyvagin, because we know that over the anti-cyclotomic tower, there's all these interesting new arithmetic phenomena related to the presence of Heegner points as you go up the tower. And the first modest consequence of this project that we did together was that we were able to give a proof of, or to extend that result we had obtained in our first 2 years of graduate school to the setting of analytic rank 0 rather than analytic rank 1, which strangely is a little bit more difficult, or was a little bit less immediate. And the reason is that, of course, if the L function of E over K twisted by chi doesn't vanish at the center, then there are no Heegner points. You've put yourself in a situation where there aren't any Heegner points, and then the methods of Kolyvagin don't immediately apply. But then the idea was that by invoking suitable congruence between modular forms, one could pass to an auxiliary form that was at least congruent modulo P to the n, and where the sign in the functional equation changed, and then applied the methods of Kolyvagin there. So it was basically blending Kolyvagin's descent with these ideas that I had learned from reading Wiles about congruency between modular forms that led us to the analytic rank 0 case of this early result. I mean, we were quite pleased by that, but still the basic framework is based on the theory of complex multiplication and the ideas of Kolyvagin. And so, yeah, that's what I say here. The proof is based crucially on congruences. And this kind of result and technique was generalized by many people later, notably Matteo Longo, Yetian, Zhou Zhang, etc. Now, another thing that came out of this project to understand the anti-cyclotomic p-adic L functions and Mazur, Tate, Teitelbaum style conjectures was a formula in the style of Rubin-Perrin-Riou. And that's the first thing that I think really pleased us in this project. Namely, we were studying a so-called anti-cyclotomic p-adic L function, which we can think of as an object that lies in the Iwasawa algebra of this profinite group, the Galois group of the anti-cyclotomic ZP extension, which I call K infinity, of the quadratic imaginary field K. So this G infinity is essentially isomorphic to ZP. And the p-adic L function belongs to the associated Iwasawa algebra, the completed group ring of this profinite group. And the theorem that I proved with Massimo, I guess around 1998, was that the first derivative of this anti-cyclotomic p-adic L function is related up to an explicit fudge factor to the square of the p-adic logarithm of a global point on the elliptic curve. So on the one hand, and this point was obtained from Heegner points. Okay, so of course the setting immediately suggests that, since we're working in this anti-cyclotomic setting. And therefore, this result can be viewed as a p-adic analog of the Gros-Zagier formula, although it wasn't the more natural analog that had been obtained much earlier by Perrin-Riou, where a cyclotomic derivative is taken and the p-adic heights of the Heegner points appears. This one was one which had, of course, much more the flavor of these formulae of Rubin and Perrin-Riou. So it could also be viewed as an anti-cyclotomic analog of these formulae. And I think the thing that struck me the most about this formula is that I had in mind at the time a close analogy between Heegner points and sort of geodesic cycles on the upper half plane, which are attached to narrow ideal classes in real quadratic fields. And so it seemed that formally, this result that I had obtained with Massimo, which was extremely explicit and concrete, could formally extend to real quadratic fields. And that, of course, is very tantalizing because there we didn't have any theory of complex multiplication to explain it. However, a problem about this, so this was sort of what was my first pass through the notion of what later I called Stark-Heegner points. And the problem, though, is that there is no anti-cyclotomic ZP extension of a real quadratic field. Because if you take the maximal sort of dihedral type as extension, ramified only at p and of p power degree of a real quadratic field, you get a finite degree extension. Because the fundamental, when you look at the description by class field theory, the fundamental unit of the real quadratic field, or the topological closure of the group it generates, sort of eats up everything but a finite quotient of that Galois group. So one way we could try to deal with that was to consider certain auxiliary extensions obtained by introducing auxiliary primes. And that was an idea that was kind of natural in light of the Taylor-Wiles method. So if we could let K infinity L be an extension which was slightly larger than the K infinity, namely, we allowed extra ramification at L in addition to the prime P. And well, this group G infinity L, I mean, we only allow P power ramification. And so this was still a finite group of P power degree. And so we had this kind of p-adic L function, if you want, which belongs to this finite group ring. And one could think of this as a kind of a stub of the p-adic L function, or of the sort of a hypothetical, fictitious p-adic L function attached to the non-existent anti-cyclotomic ZP extension of the real quadratic field. And then I formulated a conjecture about this, which was inspired by the tame refinements of Maser-Tate, which is that there's a global point on the model V group over K, for which if you take the derivative of this group ring element, and the derivative is just to be interpreted as an element in this finite group, because when this L function vanishes, it means that it belongs to the augmentation ideal, and its image modulo the square of the augmentation ideal is what we view as an algebraic avatar of the first derivative. And so that belongs canonically to this G infinity L, which has a description in terms of class field theory. It's closely related to a finite quotient of the multiplicative group of Kp star. And so if you take this derivative and you divide it out by some factor depending on L, which is essentially the L Fourier coefficient of the modular form attached to E, then and you take a limit as L goes to infinity, you get the log of a point, of a global point. Now, when I say take this limit, you have to take it over a suitable sequence of primes, which are becoming congruent to -1, in this case, modulo higher and higher powers of p. And then this thing kind of converges eventually to something p-adic. So this is a bit reminiscent of the kind of p-adic patching that you see in Taylor-Wiles. And it was, I mean, of course, the whole idea of looking at these derivatives of elements in finite group rings came from these tame refinements of Maser-Tate. So I published this conjecture. I produced some numerical evidence. So at the end, I had done a lot of computer calculations. I was convinced that the conjecture was true. And I published it in this proceedings of a conference in Trichy. But I was very unsatisfied by this conjecture because the whole formalism was a bit cumbersome, and it was very hard to really, for example, I couldn't, in a nice way, get points defined over genuine abelian extensions of the real quadratic field, which was really what one wanted to get out of this theory. So a few years later, maybe around 2000, I found a much more convincing construction of these points, which was more genuinely p-adic and didn't rely on this crutch of auxiliary primes. And so, so to motivate that, I mean, and now here I'm going to be a little bit anachronistic. I'll kind of give an account which sort of reflects a posteriori understanding. I don't think I was quite that lucid in 2000. So there's a comment that Milne, in his book on complex multiplication, writes that he says, philosophically, one expects that with the exception of the rationals, one can never obtain abelian extensions of totally real fields by adjoining special values of automorphic functions. And I think that's actually true. I believe that as well. And so one has to ask, what could play the role of automorphic functions in the setting of, if you wanted to generate abelian extensions of real quadratic fields? Now, an automorphic function is something like an L2 function on a quotient G of R mod gamma. Gamma might be G of Z or a congruence subgroup of that. And you can think of that as being contained in this set of gamma invariant functions, certain gamma invariant functions, continuous on the real points on G of R. So the loose idea is that perhaps in some cases, the higher cohomology of suitable function spaces on this symmetric space, G of R, or perhaps on the adelic symmetric space, G of the adels, or maybe on a p-adic symmetric space, G of QP, might be able to supply the necessary extension of the notion of automorphic function. So that was kind of the very vague idea. And this, initially at least, it seemed to be a little bit more tractable to develop this idea, but not absolutely indispensable to develop it in the setting of p-adic symmetric spaces. So when we work with the QP points of the group somehow. And so I'll kind of present the simplest prototypical example of these conjectures, which involves a p-adic symmetric space, just known as the Drinfeld upper half plane, which is the complement of the projective line over QP inside the projective line over CP. And there's a group gamma, which is the group of 2x2 matrices with entries in the p integers in Z of 1 over p with determinant 1. Now, that group gamma acts on HP by Mobius transformations, but it doesn't act discretely. The orbits are rather large and dense in the rigid topology. And also the first cohomology of gamma is not so interesting. I mean, this group gamma behaves a little bit formally like the Hilbert modular group. It has a rather uninteresting H1 and a much more interesting H2. So the H2 represents in some sense the interesting cohomology. Namely, the group gamma can be expressed as an amalgamated product of two copies of SL2Z, the standard copy and the conjugate by a matrix P001, which are, intersect in a common gamma naught of P. And this basic group theoretic fact, which lhara proved, I think, by exploiting the action of gamma on the so-called Brouat-Hitz tree of the p-adic upper half plane, allows us to relate the second cohomology of gamma with values in Q to the first cohomology of the Hecke group that arises here, the group gamma naught of P. And this isomorphism is an isomorphism which respects the action of Hecke operators. So modularity tells us that if we have an elliptic curve of prime conductor P, then it corresponds to an eigenclass in this H1. This H1 gamma naught of P is a very familiar object as a Hecke module. The systems of Hecke eigenvalues one picks up are essentially correspond to weight 2 modular forms of level P. And so if we have an elliptic curve of this conductor P, we can pick up a Hecke eigenclass in the second cohomology of gamma with values in Z, which has this associated system of Hecke eigenvalues. There are even two fundamentally distinct such Hecke eigenclasses corresponding essentially to the plus and minus periods of the elliptic curve. Okay. So one can then trivialize this two-cocycle alpha E, which is associated to E. And so the idea here is we're going to trivialize it by embedding it in making it take values in a much larger module, which I'm going to denote by A star. It's the multiplicative group of non-vanishing rigid analytic functions on the p-adic upper half plane. And I'll let Q sub E be the Tate period of the elliptic curve. So this elliptic curve has conductor P, so it has multiplicative reduction at P, and therefore there's a Tate period associated to it. So I can take this Tate period and I can raise it to the power alpha E. And that gives me now a two-cocycle with values in Q to the Z, but which I embed then in A star in a natural way as a constants. And I want to realize this two-cocycle as some image of a one cochain under the connecting under the D map. Okay, so the theorem is that this class Q to the alpha E becomes trivial in the second cohomology of gamma with values in A star. In other words, there's a one cochain with values in A star, which trivializes this QE to the alpha E gamma 1 gamma 2. Okay, so you get this kind of relation here. And this theorem, I was very pleased with it because it shows that the modular symbol this two-cocycle somehow knows about the Tate period of the elliptic curve, which suggests that this object has a bit of geometric content. And this theorem turns out to be a formal consequence of the conjecture of Maser-Tate-Teitelbaum, the p-adic Birchner and Dyer conjecture, which I alluded to before. And that was proved by Greenberg-Stevens, I think, around 1990 or 1989. So that was another actually important result that emerged in the period when I was a graduate student at Harvard, although it took me a bit of time really to appreciate and understand that result. Okay, so in some sense, one could say that this theorem was proved 10 years before it was stated. So it wasn't the proof that was hard here, it was really just coming up with this statement. Now, if you look at this relation, this relation that I wrote out here again, that I reproduced, it tells you that this function JE, it's a one cochain in values in A star, but if you reduce it, after all, this alpha E is taking values in Z. So on the right-hand side, you have elements in Q to the Z. So if you project this one cochain to A star mod Q e to the Z, it becomes a one cocycle, becomes a class, and you can take its class in the H1. And this class is what we call the rigid analytic cocycle attached to the elliptic curve E of conductor P. And the main interest of this rigid analytic cocycle is that it can be used to produce, at least conjecturally, these kind of interesting points that I alluded to in one of my early slides. So if tau is a general point on the p-adic upper half plane, there's always an evaluation map at tau, which sends the group of analytic functions to CP star by sending a function to its value at tau. Okay, so that evaluation map induces a map on cohomology. You map A star mod Q to the Z to CP star mod Q to the Z by evaluating at tau, but you have to be careful because, of course, this evaluation at tau is not at all compatible with the action of gamma. But it is equivariant with respect to the action of the stabilizer of tau in gamma. So we really get a natural map to the H1 of gamma tau with values in CP star mod Q to the Z, where gamma tau is the stabilizer. of tau. So if this stabilizer is trivial, which is what happens for most taus on the upper half plane, then this construction is not interesting at all. But it is non-trivial when the stabilizer is cyclic. And that happens precisely when the field generated by tau is a real quadratic field. And that led us to define the value of the rigid analytic cocycle at tau to be simply what you get by taking this cocycle, evaluating at the automorph, this gamma tau, which is a generator of the stabilizer group, taking the resulting analytic function and evaluating it at tau. Okay, so that gives you a numerical invariant in Cp star mod q to the z. And this is what we call the value of JE at this Rm point. And so that was what led us to Stark-Heegner points. I mean, the general principle is that these Rm values should provide an appropriate, although we still don't understand it at all satisfactorily on a conjectural level, substitute for Cm values of automorphic functions. So the conjecture that I formulated around 2000 is that if tau is an Rm point, then JE of tau gives rise to a global point on the elliptic curve defined over a suitable ring class field of K, depending on some associated order of tau. Now, these Stark-Heegner points ought to behave in many key respects exactly like the Heegner points over ring class fields of imaginary quadratic fields. So for example, they should satisfy an analog of the Gross-Zagier formula. They should be of infinite order precisely in rank 1 scenarios, which is both good news. I mean, we have some kind of understanding of when they're non-trivial, but also bad news because we run again into this fundamental limitation of all these constructions that we manage to say very little about the virtually desired conjecture in higher analytic rank, even with these new constructions. Okay, so another thing that was nice about these constructions is that they led to very concrete computer algorithms for computing points. So we could check them numerically in a very convincing way. So for example, here's one. So I think I wrote some programs with Rob Polak, who helped me incorporate some wonderful ideas of his and Glenn Stevens on the overconvergent modular symbols. And that gave rise to really good algorithms. So for example, here we take the real quadratic field of class number 1, which is Q joined the square root of 101. And if we evaluate the analytic cocycle attached to E at this real quadratic point, we get some p-adic numbers. And here we evaluate them modulo 11 to the 200. And one can recognize the coordinates as being certain algebraic points. Namely, x is this integer, y is this element of q square root 101, and the denominator t is given by this number. And when you plug these values into this thing, you find that you have a global point on the elliptic curve defined over that real quadratic field. And the fact that one gets such a large point, it sort of is convincing evidence that that conjecture had to be true. And second example, if we work with the elliptic curve of connector 37, which is the first curve of analytic rank 1 over Q. Well, we could take a real quadratic field like Q square root 1297, which has class number 11. So here I, on purpose, took a real quadratic field of relatively small discriminant, but large class number. And then one can evaluate the value of the associated cocycle at some real quadratic number like this. And one gets the point whose x coordinate, for example, satisfies a degree 11 polynomial like this, at least up to the computed 37-adic accuracy. And this polynomial turns out to generate the Hilbert class field, and it leads to a construction of global points over this degree 11 extension. Okay, so there was sort of at that stage, we given the experimental evidence that we could obtain for this conjecture, it was completely clear that the conjecture was true, but we really lacked the theoretical notions to actually give much theoretical evidence for it. So in the period after formulating this conjecture, roughly 2001 to 2006, I had two really wonderful collaborators who were, like me, very interested in the Stark conjectures. So Pierre Charolois and Samit Dasgupta. And together we thought about relations between these Stark-Heegner type constructions and Stark units and p-adic analogs that grew out of a conjecture formulated by Gross. And so I met Samit for the first time in 2001 at a conference in Orlando. And Pierre, about a year later, at a conference in Baltimore, which was about Stark's conjecture. Both of them were at McGill in the period 2005-2006. They both spent some time there. And I remember that period as being a particularly pleasant and fruitful one for thinking about Stark's conjecture. So Samit wrote his thesis in 2004, which essentially studied an analog of the elliptic cocycle I spoke before, but an object which is more analogous to modular units or Eisenstein series, so the Eisenstein counterpart. So the idea here is that this H2 of gamma z also contains a class which is in the Eisenstein subspace on which the Hecke operators act as on the Eisenstein series. And this so-called Dedekind-Rademacher cocycle in the H1 just encodes the periods of the modular units, delta of pz over delta of z, which is a modular unit of level p. With Samit in 2003, and here I'm giving a slightly more general modification of our original statement that was obtained later by Alice Pocci and Jan Vonk. It says that there's one cochain on gamma with values in A star, which for all gamma 1, gamma 2 in gamma satisfies this relation. Okay, so it's exactly the same relation as we had before for the elliptic cocycle, except that instead of the Tate period, you have just the prime p, and instead of the elliptic cocycle, you have this Dedekind-Rademacher two-cocyle. And so, well, we can then look at the RM values of this so-called Dedekind-Rademacher cocycle in the H1 of A star with values in p to the z. And now, since it takes values in A star mod p to the z, and p is a perfectly good rational number, it makes perfect sense to ask for the rationality of these values. And the conjecture that Samit and I formulated around 2003 is that the RM values of the Dedekind-Rademacher cocycles are global p units in the ring class field of K associated to tau. And we could also prove a kind of Kronecker limit formula for this RM value, which relates the value of this Dedekind-Rademacher cocycle to certain p-adic L series. And the p-adic L series are the Deligne-Ribet p-adic L functions attached to the real quadratic field K and eventually to some ideal class or some narrow ideal class in K. So they're partial p-adic L functions. And more precisely, if I denote by J Dedekind-Rademacher plus the norm from QP tau to QP, so from this quadratic extension of QP of the Dedekind-Rademacher value at tau, then the theorem is that this quantity, the p-adic logarithm of J Dedekind-Rademacher plus of tau, is equal to the derivative of the Deligne-Ribet p-adic L function attached to this ideal class. And therefore, well, one could say something about its algebraicity. The algebraicity was actually a consequence of the p-adic Gross-Stark conjecture. And that kind of connection led us to being very interested in the Gross-Stark conjecture. And with Rob Polak, a few years later, we gave a proof of the Gross-Stark conjecture. And so we proved that for all totally odd characters, even of generally totally real fields, the p-adic Gross-Stark conjecture is true. So the relation between the first derivative of the p-adic L function and these logarithms of algebraic numbers of p units. Now, one point one should make here is that this p-adic Stark conjecture formulated by Gross is much more tractable than the original Stark conjecture, on which we're still completely stuck. So there's something quite a bit deeper about the Archimedean setting. And the reason is that the algebraic numbers that emerged from the Gross-Stark conjecture are p units rather than genuine units. And these p units actually arise naturally when one studies the p-adic deformation theory of certain classical modular forms, Hilbert modular forms actually over the totally real field. And so again, the key ingredient in this proof of the Gross-Stark conjecture was the deformation theory of, in this case, Hilbert modular Eisenstein series and their associated Galois representations. And that direction has been developed much further later by Pierre and Samit, who introduced extensions of these kind of constructions to the setting of GLN. And then Samit and Mahesh Kakde, who've done wonderful work on tame refinements of the Gross-Stark conjecture. So it's been a fantastic amount of recent work in this direction, which I won't have time to do justice to in this lecture. Would be the topic for another talk, but I do want to say that these successes in this direction continue to put Stark's conjecture in the center of a very important approach to explicit class field theory based on the leading terms of p-adic, of L functions, p-adic and classical. Okay, so after this work, in some sense, I branched out a little bit. I diverged. I became more interested in what might be the geometry underlying these rigid analytic cocycles, both the elliptic and the Dedekind-Rademacher. And this is a conjecture that I still don't really have any satisfactory answer to at all. But in the period between 2006 and 2015, I had other new collaborators like Kartik Prasanna and Victor Roger, who kind of in some sense nudged me towards somehow an attempt at a more geometric approach to this theory of Stark-Heegner points. So there's a strong analogy between Stark-Heegner points and Abel-Jacobi images of algebraic cycles. This is something I really learned from Kartik, from my interactions with Kartik. And then later with Victor, we started thinking about the arithmetic of triple products of modular forms. And that ended up leading to a lot of progress, or some progress, I should say, on the theory of Stark-Heegner points. So in general, when one looks at a triple product L function where F, G, and H are classical modular forms of, say, of weight 2, and one can produce an algebraic cycle that says something about the leading term of this L function in the spirit of the Bloch-Kato conjectures. But I wasn't very interested in the arithmetic of this rank 8 motive, which is the tensor product of 3 representations attached to modular forms of weight 2, because that has nothing to do with the Bertrand and Dyer conjecture. It's a more exotic kind of a motive, if you want. And so I'm very grateful that Victor kind of persevered and insisted that we continue to think about this triple product motive, because we saw later that it was actually closely connected to the BSD conjecture by the miracle of p-adic variation. So namely, if we have a construction of an arithmetic invariant attached to a triple of modular forms of weight 2, then one can insert these modular forms of weight 2 in a Hida family, in a p-adic family of modular forms, and deform the construction from weight 222 to weight 211, where one now has an elliptic curve, for example, and a pair of Artin representations attached to classical modular forms of weight 1. And then this resulting class, which is not obtained by a geometric procedure at all, because it involves this p-adic deformation, becomes very relevant to studying the BSD conjecture, or the equivariant BSD conjecture for certain Artin representations. And so then this led to a theorem exploiting these p-adic families of diagonal cycles, which now involves finally a real quadratic field. And the theorem that I proved with Victor around 2011, 2012, is that if chi is a character now of the Hilbert class field, this real quadratic field, and if the twisted L value is non-zero at the center, then the corresponding component of the mod LV group is trivial. And so this is an exact analog of that very minor result that I had obtained with Bertolini when in our second year of graduate school, which was the case where K is a quadratic imaginary field in analytic rank 1, and then later using congruence is extended to analytic rank 0. Okay, so these two results, which really just rely on Heegner points, and I had been convinced for a long time that a proof of the corresponding result over a real quadratic field would have to pass through significant progress on Stark-Heegner points. But here in this result, we bypassed, still don't understand really Stark-Heegner points, but we were still able to prove this kind of result. So that was this result that I proved with Victor. However, the counterpart of this analytic rank 1 result for real quadratic fields still remains very, very mysterious. So using these p-adic deformation techniques, we can construct certain cohomology classes, which give rise to elements in the Selmer group and are related to Stark-Heegner points. But constructing elements in Galois cohomology and in Selmer groups is much less deep and difficult than constructing actual global points. And on that key question, we're still completely in the dark. So that's the situation. And I should say that the proof of this theorem really involves transposing a method of Cato, which it sort of took me a long time to understand this connection, but it really is an extension of Cato's method, replacing his so-called Balance and Cato elements by certain diagonal classes in p-adic families. Okay, so now I'll talk a little bit about, I guess in my remaining 10 minutes or so, what came after that. I mean, so it's natural when you think about rigid analytic cocycles to think about whether there might be objects that play the role of meromorphic modular functions rather than modular forms. And so it's natural to consider the M star the multiplicative group of rigid meromorphic functions, of which there are a lot more than rigid analytic functions. And we say that a rigid meromorphic cocycle is a class in the first cohomology of the lhara group with values in M star. And these are objects that I started to study with Jan Vonk in 2017, roughly, 2016 maybe. And from the outset, we had some clues that this notion might be fruitful. Maybe the most important one was a conjecture by Bill Duke and Yinkun Lee, which really inspired me tremendously. It was very inspiring for me at the time, which says that the Fourier coefficients of certain weak harmonic mass forms are logarithms of interesting algebraic numbers. And it was immediately apparent that one could formulate a p-adic analog of this conjecture, which related the Fourier coefficients of certain p-adic deformations of a so-called Rm theta series to p-adic logarithms of Q units in the Hilbert class fields, with Q not equal to P. And this kind of formula was very important because when you look at p-adic L functions in the spirit of the Gross-Stark conjectures, you realize the leading term of p-adic L functions only know about p-adic logarithms of P units. And so the Fourier coefficients of these p-adic deformations of modular form carry richer arithmetic information because they also know about the p-adic logarithms of Q units for Q not equal to P. So that was the first time that we thought that by some kind of conceptual analytic approach, we might be able to obtain genuine logarithms of general algebraic numbers. And so, well, I mean, we formulated the conjecture, or I mean, as a theorem actually, classifying these rigid meromorphic cocycles. And we found that actually the divisors, so if you have a class in this H1 with as an M star, then the value of such a J, for every tau in the Rm points of HP, there's an essentially unique meromorphic cocycle whose divisor is supported on the gamma orbit of this tau for all gamma and tau. So there's an intimate connection between divisors of rigid meromorphic cocycles and Rm points. And that was, that grew out of ideas of Marvin Knopp, Youngju Choi, and Don Zagier on rational period functions. We can think of these as kind of a p-adic completion of the notion, of the more algebraic notion of period functions. And in writing down explicit formulas for these cocycles, we were also guided by a work of Duke, Özlem İmamoğlu, and Arpad Toph on so-called modular cocycles and linking numbers. Okay, so finally, once we had these rigid meromorphic cocycles with divisors supported on certain Rm points, we could look at their values, the value of J tau 1 at another Rm point tau 2. And this is a p-adic function of two variables, tau 1 and tau 2, two Rm points. And it satisfies a certain anti-symmetry relation. And the conjecture is that this behaves in all key respects exactly like the difference of singular moduli as were studied in the work of Gross and Zagier for tau 1 and tau 2 CM points. Here, J is just the usual modular J function. And so, namely, we expect that they belong to the right composita of narrow ring class fields of real quadratic fields and that they admit explicit factorizations, exactly as in the work of Zagier. And so, well, okay, there's a lot of experimental evidence for this conjecture. Again, one can check these conjectures quite convincingly on the computer. But in contrast with the notion of Stark-Heegner points, here there's a growing body of theoretical evidence about the algebraicity of these singular moduli. And that's again based on the same tool, I mean, the study of p-adic deformations of modular forms. And so there are some ongoing projects, I mean, some works that are already finished with Alice Pozzi and Jan Vank and some other ongoing projects that seek to prove this algebraicity in more and more general settings. So whereas these Stark-Heegner points are very much still very mysterious, we see bright prospects for proving the algebraicity of these differences of singular moduli. Okay, so now I'll finish. So the closing remarks. So this path that spanning over 30 years, that's led eventually to this theory of RM singular moduli has been very roundabout and tortuous, and involved a lot of false starts and dead ends and misconceptions, and also long periods of being stuck. But it was also very enjoyable and also far from a solitary journey. And I'm very grateful in particular to all the mentors whose ideas that I evoked at the beginning of the lecture launched me in these fruitful directions. So of course, Dick Gross and Andrew Wiles were my official mentors and at Harvard and Princeton in these early years. And then people like Tate and Mazur, of course, who influenced me as they influenced all of us. And Carl Rubin, Rubin-Perrin-Riou, Ralph Greenberg, Glenn Stevens, whose important ideas were really instrumental to setting up this theory. And also, I've been frequently helped by this long list of close collaborators who've often kind of dragged me a little bit out of my comfort zone and led me to understand new things. So Bertolini, Jovita, Dasgupta, Charolois, Logan, Prasanna, Rocher, Lauder, Vank, and Pozzi most recently have all been wonderful collaborators. And so I want to just finish by thanking all of them for all that I've learned from them over the years, all the inspiration they've provided me, and thanking you all for your attention, and apologies for having run a little bit beyond my allotted time. Thank you.
Thank you. Are there any questions for Henri? So I was wondering actually about, so how did you, so you started working with Bertolini when you were a graduate student. So how did that come to be actually?
Well, yeah, we were both students of Gross actually at the time. I mean, Massimo was 1 year ahead of me at Harvard, and and then I remember my first summer at Harvard, we spent a long times just doing reading seminars together. That first summer I was at Harvard, there was also a very nice seminar at Brown, I think, on the work of Rubin. And so we were taking the bus every day to, I mean, several times a week to go to Brown and listen to these lectures. And then eventually, yeah, I mean, that's how we, afterwards, Massimo moved to Columbia and started working with Carl Rubin. So we were,
right.
It's certainly very helpful, I think, especially at the beginning of one's career, to have close collaborators who really share common goals. Otherwise, doing mathematics can be a bit lonely and depressing.
Yeah, I guess that's one thing that's been notable in your work. You've had quite a few collaborators who you've sort of repeatedly written a lot of papers with over many years. Yeah.
Yeah, that's right. Yeah, I mean.
Yeah.
Yeah.
Anybody have a mathematical question?
Yeah, so thanks, Henri, for this inspiring talk. So what is the, what the relation between the Stark-Heegner points and this later thing you talked about, RM moduli? What is the relation? Is there a relation between these two instructions?
Well, so of course, the framework suggests, the notion of RM singular moduli was very much motivated by this framework of rigid analytic cocycles. And I guess you should think of it as, yeah, I mean, the rigid meromorphic cocycles are really the analog in this theory of meromorphic modular functions. So if you have a modular function, or if you look at, you can ask yourself, if given a divisor on the upper half plane, when is it the divisor of a modular function? Well, it is if the corresponding divisor is trivial and Jacobian, right? So the class of the divisor in the Jacobian represents an obstruction to the existence of a meromorphic function. So likewise, if you have an RM divisor, which gives rise to a Stark-Heegner point, you can ask what kind of consolation prize you would get if this Stark-Heegner divisor happened to be trivial in the Jacobian of the modular curve. And the answer is that you would get this rigid meromorphic cocycle. So the obstruction of RM divisors being principal in that sense is exactly given by the Stark-Heegner point. But the advantage of working with these rigid meromorphic cocycles is that one has a lot more tools to handle them. One can try to understand their algebraicity on a theoretical level. In a sense, the analysis is based on extending the work of Zagier on factorizations of differences of singular moduli. Now, this paper of Zagier is very interesting because it approaches this factorization from two different angles. So there's an algebraic proof and an analytic proof. And the algebraic proof is based on the theory of complex multiplication, on the fact that CM points have a moduli interpretation, and one can understand the factorizations in terms of the theory of elliptic curves with complex multiplication. But then there's a wonderful analytic proof, which makes absolutely no use of the theory of complex multiplication, and just constructs a modular form, a non-holomorphic modular form, whose image by the holomorphic projection gives rise to, the coefficients turn out to break up into two contributions. One is a finite sum of logarithms of algebraic numbers, and the other is something which, when you examine it, you realize is just the difference of singular moduli itself. And so if you put yourself in level one, this modular form is trivial, the Fourier coefficients vanish, and you get the identity. And it's that analytic approach in Zagier that we're mimicking to prove the algebraicity of these RM singular moduli. That's kind of so they are definitely easy. We understand these objects better in some sense, although we completely lack what's the counterpart of the algebraic approach in Zagier.
So why the 5 primes actually in the result was bonk? What?
Yeah, so that I'm sorry, I was a little bit rushed and I didn't really, I think, yeah, so where it was there, it was in the previous one, right? Yeah, so what's special about these primes is that they're exactly the so-called genus 0 primes, for which the genus of the modular curve x naught of p is 0.
Okay.
And this genus represents an obstruction to arbitrary RM points being principal divisors. So for general primes, one has to take such a tau and maybe hit it with some Heck operator that would annihilate a finite dimensional space of modular forms of weight 2 in level p. And so one gets less rigid meromorphic cocycles. So this was just for ease of, and so one only has differences of singular moduli for these primes, but that which is completely similar to the fact that we only have a convincing Haupt module for modular curves of genus 0.
So I know you're interested in these RM points, but when you did this deformation approach with Lauder and Roger, did you ever go back and see if these triple product L functions specialize to the imaginary quadratic case?
You mean the deformation theoretic?
Yeah.
That's an interesting question. I think some things have been done, but there would still be interesting questions there. I mean, the basic thing that we look at is a kind of Eisenstein series attached to a character of the real quadratic field. And in the Gross and Zagier's work, they consider an Eisenstein series attached to a genus character, to an odd genus character of a real quadratic field. And they do something in the Archimedean setting. But it would be very interesting to go over the original calculation of Gross-Zagier involving an odd genus character, but with p-adic families of Eisenstein series. I expect the calculations there would be much simpler than in the original calculation of Gross-Zagier, and we would yield results of a similar flavor. So it would be something worth doing. But we were mainly interested in non-quadratic characters of the real quadratic field, because that's where we really get substantial applications to explicit classical theory.
Okay, if there are no other questions, thank you, Henri, for a fantastic talk.
Okay, well, thank you for your invitation. It was a pleasure, and